Hello everyone, welcome to this tutorial. My name is Emerson Ahari. I'm a Google Earth Engine expert. In this tutorial, I'm gonna show you how to deal with PM2.5 in the Google Earth Engine platform using Colab and Python programming language. As you can see, in this tutorial, I'm gonna show you how to plot monthly variation of PM2.5 for a big region. And also I will show you how to convert the data from hourly frequency to the daily format and the monthly, how to plot the monthly variation or daily variation for a single point. And also you will understand about how to get a statistical information from each image. For example, from an average image, how to get a statistical information that could be really beneficial to get more insight about PM2.5 variations. And I will show you how to use Earth Engine libraries in the Python programming language, such as Xee, that is developed by the Google that allows you to convert the image collection format to the Xarray structure that is very beneficial to integrate machine learning techniques and satellite data. Okay, now in the first step, make a new Colab environment. Go to the Colab environment. It's very easy to do. Just go to colab.research.google.com, make a new notebook, and then start coding. It is very easy to work with the Colab. Only one Gmail account is necessary, and then you can start coding without any issues. You can call all the Python libraries easily here, or you can install it without any challenge. It is based on the cloud environment, and easily you can make a connection between Colab and Earth Engine platform. Let's set a name for your code. For example, my code name here is GEE0012 and PM2.5. 2.5. There it is. In the first step, you must call Earth Engine libraries using Python. Import EE or Earth Engine library, and then import Xarray library, Xarray as XR. Alt Enter, go to the next cell. The first cell is under process. First, Colab is connecting to the servers. Once the connection is done, you can see the library starts to run. So, the first cell ran successfully. In the second one, we need to call Xee. As you can see, the Xee is a library developed by Google developers that allows you to integrate Xarray structure with the collection format in the Google Earth Engine platform. So, as it is not built-in available in the Colab environment, install it first. Pip install. The library is Xee, and then import it as a single library into the code. Let's run it again and make a new code. You can see it's installing without any challenge. It is very easy to work with Colab environment and also shifting between libraries or installing new libraries. So, in the next step, we need to make a connection between Earth Engine and Colab environment. As you can see, here there is an instruction that shows you how to make this connection. First, make authentication, and then, because through the authentication, you need to introduce your Google account to connect to the Earth Engine, and then initialize personal Earth Engine accounts. So, first argument is a project name. What is the project name? The project name refers to the name of the cloud environment or cloud project that you already defined for your Earth Engine account. But the question is how to understand or how to find it for your own personal account. It is very easy to find. Just go to Earth Engine account in the code editor environment. Upper right, there is a button here. Click on and then project info. The project info shows your own or your personal cloud projects. For myself is like this, and then for yourself is different. Copy and paste it into the code just like this, because through the project name we can make this connection. Back to the XEE, and another parameter argument here is the OPT URL. Just copy and paste it. That is necessary to deal with a high volume data in the Colab environment. So let's run the code, and after a few moments you will see a pop-up that asking you to connect to your Earth Engine account through the Gmail address. Click on OK, and after a few moments connection is made, and then you can write your Earth Engine script here without any challenge. So everything is done and we have no issues. In the next step, I'm going to show you how to call your desired data into the Colab environment. For example, I already found the PM2.5 data from Mera2 dataset RSL diagnostic through the Earth Engine data catalog. Here, the Earth Engine snippet, including an ID that allows you to call this data in the Earth Engine environment. So, make a new variable as collection equals to the image collection format. There it is. Select the target band. So, as you can see, several bands available here with their description. The description allows you to find your target band easily. For example, my target band is about dust scattering or PM2.5 scattering. So let's find it first. Yes, as you can see, dust scattering based on aerosol optical thickness PM2.5. So let's select and copy and paste it into your code. There it is. So let's run the collection. We just call the data and the target band, nothing more. This data provided PM2.5 with hourly frequency. That is a large number of data. As you can see, it has hourly frequency. So it is very hard to deal with such kind of huge data set. I found a solution and I want to and I'm going to address it here, that allows you to deal with such kind of data much easier thanks to the Earth Engine capabilities and XEE library. So first of all, we need to convert the hourly data to the daily frequency. In the most of investigations, we need to understand how the daily how PM2.5 varies from one day to another day to detect some, for example, dust storm that happening in the arid or semi-arid region. So in the first step, we need to use Earth Engine script to convert the hourly data to the daily format. It is very easy to do. So first, define the time start and time end. For example, you can select a period of time you want to do process based on. Earth Engine.date allows you to convert a string to a date. For example, the target year is 2008. Time start and time end equals to 2008 and 2009. 2009, there it is. Then we need calculate number of days between time start and time end. So time difference, another variable. From time end, there it is, calculate the differences until time start based on a unit. The unit is days. The number of days is matter. So the next is we need to make a list of days with their date actually. Time list equals to searchengine.list.sequence. As you can see, list is starting from 0 to the numbers calculated by time difference. Let's convert it to the round as an integer to avoid any float or actually wrong numbers. So EarthEngine.number converts the time difference to a number and then subtract it from 0. Subtract from 1, sorry, my mistake. So now we have a list starting from 0, for example, to 365 or 366, depends on the year. So I started from 0 and subtracted from 1. In the next step, we need to replace the values, the number of the days, with actually the actual date here. So it's very easy. Define a loop through the map. Through the lambda, you can actually apply a function or a kind of process on each value separately. Each input is, for example, day number or day interval equals to from time start already defined above. We want to go advanced based on interval defined. So with daily frequency, there it is. The unit should be days. Time list is also created. In the next step, we need to actually filter our collection based on a time list and then get an average. As we have large number of data, for example, couple of images per hour, per day, we want to, for example, aggregate them to the daily average. So let's make a function def actually start a function, and the function name is daily aggregation. The function has an input. The input is date. We already made a list of available dates, and then in the functions I'm gonna show you how to do the aggregation. First of all, for each date we need to define a time start that shows the day begins, and a time end that shows the day is end. So now the start date equals to get the input date as a date format, and then end date equals to go from start date to advance with 1 day interval like this. Okay, now for each existing date, a start and end defined. Now we need to filter the collection based on new start and the new end. So now the daily image equals to get the collection image and filter it based on a start date and end date. There it is. And calculate the average or aggregated to the temporal spatio-temporal average through 24 hours. So for each pixel, the average value calculated. Now we will have one single image per day that shows average PM2.5 per pixel. So function returning a result that is image with new system time start information. System time start, that is start date with millisecond format. Why millisecond? Because the Earth engine calculates based on or works based on millisecond format, not the normal format. Okay, let's run a function. The function is raw and also not working now. We need to apply the function, the daily aggregation, on the list of dates already created. So now a new variable is daily collection equals to bring all calculation into image collection structure. From a time list, make a loop structure. For each existing time, we want to apply the daily aggregation function. There it is. Let's run the code, and now the data converted to the daily frequency. Okay, now we were doing actually scripting through the Earth engine functions. From now on, I'm gonna use Xarray and XEE libraries to convert the daily image collection into, for example, a dataset with array structure, that now I can do a different data analysis method using Xarray structure, that I'm going to show you some examples in this tutorial, such as plotting, getting statistical information, and so on. If you follow my YouTube channel, definitely you can find more. So, because there are a lot of examples in this regard. Okay, let's go on. Now I'm gonna make a data set with the array structure. From Xarray, enter the data set as an array structure. The input is daily collection based on Earth Engine, Google Earth Engine or EEE. So, and then for the input collection, define the coordinate system. It is necessary EPSG 4326. And in addition to CRS, the scale is matter. The scale is a spatial resolution. The spatial resolution is 50 kilometer approximately. That makes sense for such kind of data. But the scale should be imported with a, for example, degree unit. Each degree is 100 kilometer, and now the half of degree is 50 kilometer. There it is, 0.5 degree. And the next parameter is about the region of interest. I'm suggesting you to define your region of interest in the first step. How to define the region of interest? It is very easy to do. Just go to the code editor environment and select 2 points for your bounding box. For example, in this tutorial, I'm gonna monitor PM2.5 variation in Iran, my own country. So just you need to define 2 points, one upper left and one lower right. So through the drawing tools or marker, set 2 points like this easily. Imagine you have a rectangle and you need 2 points for that, upper left and lower right. So go to the editor environment, and here you can see the latitude and longitude for each point separately. Make a variable as location here, for example inside a bracket. First you must add the minimum longitude. The minimum longitude in these 2 points is this value. Just copy and paste it into the list structure. And then the minimum latitude in these 2 points is 24. Again, copy and paste it. The next is the maximum longitude and maximum latitude. Maximum longitude is this, and the maximum latitude is 40. There it is. We have coordinates, a list of coordinates for the bounding box. Just copy and paste it into the cell. Run the code. The location defined that should be assigned to a geometry. There it is. Just run the code, but after a few moments, you will face an error here. We need to check what the problem is. The module Xarray has no attribute open dataset. It was my mistake here. I had a typo, and here should be dataset, just like that. Let's run the code, and after a few moments, you can see the problem is solved and the data created, the daily data created. Let's check the inside the data, the data set. Here we have a multi-dimensional data set that you can see one dimension is time, another one is longitude and latitude. If you click on time, you can see the dataset available for 2008 and with daily frequency ends to the last day of December. And one variable name is scatter value, thus scatter value for PM2.5 is available, and dataset properties is also shows here. And here we have a CRS coordinate system that codes is EPSG4326. The codes actually shows WGS84 for all around the world. So you can use the WGS84 in everywhere you are working. Remember that no matter which area selected in this tutorial, this data publicly available for whole of the world, and all of you can have access to the Colab environment and Google Earth Engine account. Everything is free of charge, but you must follow this tutorial and get and actually produce PM2.5 maps for your region of interest. In the next step, I'm going to show you how you can plot the PM2.5 variation for your region of interest. For example, in Iran, most of the time we have, for example, dust issues and dust storms problem in the southern and southwest of country. So here I'm gonna select a point and see how much actually the daily PM value varies in this point or in this region. So we need to make a subset based on new coordinates. For example, make a new point equals to from the dataset select. Okay, now we need to select the data based on longitude and latitude and with a method. Method should be nearest, the nearest neighbor or nearest value to the latitude and longitude. The nearest here is okay. Enter the longitude is the first one as a number, latitude as a second one as a number. Let's run the variable and the point is created. Now I'm gonna plot the point variation. So if you run a point and see the inside, you will see only one latitude and longitude selected. Now we need to plot this single point variation with daily frequency. To do this, we need matplotlib library. Let's import matplotlib pyplot as plt. Let's run this function, run this library, and plot tools are available now. For example, I'm gonna plot the variation for that single point. do like that. Make a fig and x. From PLT, define subplots first. Fig size equal to, for example, I'm gonna have a figure with, for example, this size, 5 and 3. Let's run a code. Now you will have actually a plot, empty plot or blank plot that you can plot the PM variation inside. Okay, in the next step, just call the point data, but let's do this. X dot plot, X already defined here, dot plot, point dot time, because the point has time dimension, and point dot variable name. The variable name is like this. Let's run the code, and after a few moments you can see the variation for that point. This is the daily PM2.5 variation for the selected point. You can customize the plot based on different arguments available here. For example, if you change the 5 to 7, you can see the chart a little stretched more, and you can make a better visualization here. For example, you can change the line style to different formats. For example, dash the slide, or you can add a marker for that, just like this. Or you can increase or decrease marker size. For example, 2 or 3. You can change it easily without any challenge. Or you can change the color, for example, the orange or any other color that you prefer for your work, or even black or red, for example. There are a lot of tools you can use to visualize the plot for your region of interest. And even you can change the line style to the dots style, for example. You can see there are a lot of things that you can do here. Okay, for example, we can add a title, add a vertical name, horizontal name. It's totally up to you which kind of properties added here. Okay, in the next tutorials, in the future tutorials, I will show you how to add more things to the plot here. But just I wanted to show you how to plot your region of interest variations, PM2.5 variations. As it is suggested by AI here, if you, for example, press on tab, easily you can have X label, Y label, and plot that shows. So it is suggested by the AI assistant. Just if you press on a tab, you can have extra things. Or if you want to have, for example, the title, that set title allows you to show that this is PM 2.5 variation. There it is. Let's go to the next step. But before going to the next step, if you want to get export, just use plt dot savefig. You want to get export using savefig pm2.5.png format, and the DPI equals to 360 to have the highest quality. Let's run a code. Go to the left panel. PM2.5 PNG is available. Just download it into your system. If you want to add it into your report, it is very easy to do. Okay, here you have a high quality plot. But the problem is, as you can see, something missed here, the horizontal border name. We can actually include it in the final result using bbbox inches. Already set it as tight. Let's run a code again and hope problem solved this time. Again, save it and check it now. Yes, now you have all the parameters, all the items in the plot, in a single plot actually. Let's go to the next step. Now I'm gonna actually convert the daily data into, for example, the monthly format and visualize it. But before that, I'm gonna show you if you want to get average image for your region of interest, it is very easy. For example, already data set, the daily data set defined by the DS variable. Just call the DS again and convert it to the average image. If you want to average per time for each pixel, just do like this. DS equals to ds.min. I did a mistake. It is better to change the name. dsmin, dsmin. Yeah, because I'm gonna use with the ds. Unfortunately, actually the ds variable already changed. That caused a mistake in the further analysis. Let's go a few steps back and again call the ds variable through the daily collection and open dataset. Now check it again. Everything is fine. Okay, and also the figure works properly without any challenge. Yes, and now the average is calculating. The problem is fixed, and after a few moments you can see the final result. Yes, the average image is created. So for example, you want to plot the average image. The dsmin dot plot, the x equals to longitude dimension, y equals to latitude dimension, and what else? For example, the color map could be, for example, cool warm. If you search on the net about Python color map, you will find a lot of names and also color palettes in this regard. Okay, and if you want to skip the outliers, set robust as true. Let's run a code. Yes, there is a problem here because we already should call the variable name before the plotting. Hope problem is solved. Yes. Now you can see the average PM2.5 for 2008 with latitude and longitude and selected region with a nice legend. Higher values, higher dust particle size, and also you can see them with a red color. For example, in the southwest, in the Middle East, for example, in Iraq, Saudi Arabia, in this region, you can see the higher particle size compared to the inside area. But the other side, in the southeast of Iran, for example, in this area, there are some signs of high particle matter in this area. So now imagine that we want to get some statistical information from this average image. So the dsmin just must be converted to a data frame structure, and then we can get initial statistical information easily. The variable name is .cat, and then dot to convert it to the data frame structure, and then use .describe. The .describe allows you to see the statistical information for a raster layer. The benefit of Xarray and XEE is that you can apply the array functions on a raster layer and see the result. That is very awesome. In the future tutorials, I will show you how to apply the advanced statistical analysis to get more insight about the satellite data and products. As we are in the early stage, most of the users dealing with the Xarray and XEE, we need to understand some basic things about these functions. So here you can see the average PM2.5, standard deviation, minimum, maximum, and percentile value. That could be very beneficial for your study. In the next step, I'm gonna make a monthly plot and shows you how PM2.5 varies from one month to another month. So it's very easy to do in the Xarray. For example, if you remember, before we used couple of scripts to convert the data from hourly format to the daily format. But now, thanks to Xarray structure, it is very easy to convert the data to multi-frequency structure without any challenge. So, for example, I'm gonna convert it to the monthly structure equals to get the DS data and resample it to the monthly frequency and aggregate it to mean during the time. I'm gonna get monthly PM2.5 per pixel. Easily calculated. Let's check it together. The monthly product is created now. And as you can see, you have a data set with monthly frequency, January, February, March, and so on. Okay, in the next step, I'm gonna plot a monthly variation, very easy and without any challenge. Let's call the monthly variable, select the variable name, and use the plot. Even you can use the AI assistant by tab here suggested something. So, but I prefer to write myself because helps me to learn. It is better to use AI to learn something rather than doing something automatically. Doing automatic is fine, but in one condition, that you write that code, not it is written by AI. Try to use AI to learn new things, to fix your errors, rather than to actually run the codes without understanding what's happening behind. X equals to longitude dimension, Y equals to latitude dimension, and the column, the third dimension is time, and in each row I'm gonna have in a grid structure I'm gonna have 4 maps in each line. So the color map could be, for example, cool warm, same as before. Let's skip the outlier values through the robust. Okay, let's run a code now and see the monthly variation of PM2.5 for your region of interest. There it is. You can see in some of the months, warmer months or drier months with the less precipitation and higher temperature, we have some centers or external and internal centers of PM2.5 in Iran. As you can see here, it's higher value. It has higher values in April, in the April, May, June, and July, as you can see. But in the wet seasons, the PM2.5 decreased dramatically. Okay, if you want to get export from the figure, this is same as what we did before. So here we already used save.fig. Just you can copy and paste it here. Again, just copy and paste it. This one is PM2.5 with monthly frequency and the rest is same. Let's run a code again. Go to the left panel and after a few moments you can save your result easily. So PM monthly is available. Let's download it and now you can see the monthly data is created. Click on and see the output figure with a high quality and you can easily use that in your papers and investigations. I hope you like this tutorial, and also I'm asking you to share these tutorials with all of your friends. I'm trying to share my idea as understandings about the satellite data analysis in the Google Earth Engine platform. Feel free to share this tutorial and use this tutorial for your studies. Thank you for your attention.